Welcome. In this session on artificial neural networks, we'll form the objective function and find its gradient. The neural network that we're looking at will have a single data 1 form that is coming into a hidden layer. For now, we'll consider just 2 neurons in this hidden layer, but there could be many more, and we'll have a single output neuron. In order to get our objective, we need first a residual error. And there's only one data, one form that's coming in, so there's only one residual. If we have multiple data, we'll have to handle this separately. So this residual is a function of all of the weights in the whole network, and that we will define as the label minus the activation function for our output neuron that is a function of the linear product for that output neuron, and that is a function of all of the weights in the entire network. So our objective, there are a number of objectives that are used in neural networks. We'll stick with a sum of square of residuals. So we'll formulate our objective as we're anticipating a differentiation, so we'll put a factor of 1/2, and that will be 1/2 of the square of the residual. And then for steepest descent, what we need is the gradient 1 form of this objective function. So the first thing we can do is apply the chain rule. And the chain rule will give us the gradient of this function that has all of the weights in the entire network will be the partial derivative of the residual with respect to the activation function times the gradient of that activation function of the hidden neuron, but now it's a function of all of the weights. This is just what we had when we derived the gradient for a single neuron. So let's recall that, right? So let's recall that when we had a single neuron, that the partial derivative of its activation function with respect to the weights just of itself was, we represented that as some function c of the linear response. Now that is the linear response of that output neuron, and that is the derivative of that. It's possible that this activation function and these activation functions are different. All of those have to be the same because of our math. This one and these might possibly differ. So the derivative of the activation function with respect to the weights is the rate of change of the activation function times the input to that neuron, and that input depends on those weights. So what we can now do is we can keep applying this chain rule. So the partial derivative, so that's the partial derivative with respect to weight 1. What's the rate of change of the output activation with respect to the weights in layer 2? That is, how fast does this output change when we change the weights in the hidden layer? Well, that will be the rate of change of the activation function with respect to its linear product times the rate of change of the linear product with respect to those weights that are in layer 2. And that is simply, and we already know that the rate of change of the activation function with respect to its linear product is, we're saying that that is some function psi for that output layer that is a function of its linear product. So for this remaining term, let's write that as the linear product for this output neuron is a function of its own weights and all of the weights in layer 2. And we can write that as the weights in linear 1 transpose, let's put the transpose out there, times the one form coming into this also transposed. So we're using that observation from the previous session that we can represent a product of a one form and a vector in many ways. And so we could write that as, this is the weights for that output transposed into a one form, and then this transposed will be the outputs of the layer 2 neurons that are a function of the layer 2 weights to which we've appended a 1. And if you recall from the previous session, we defined this as being all of these little z's, and then we put a 1 on them to account for the bias term. And now all we're doing is we're transposing that. So our previous result was that the partial derivative of all of the outputs of layer 2 with respect to all of the weights of layer 2 was that diagonal Jacobian of the outputs of layer 2 times a block diagonal matrix, and that was the Kronecker product of the identity and the single data 1 form that's coming in. So now we can combine these, and now we can write this, so we can write the rate of change of the outputs of the hidden layer with respect to the weights of the hidden layer as this Jacobian. Let's redo that. We can now combine these results, and what we find is that the partial derivative of the output of the whole neural network with respect to the weights of the hidden layer is the rate of change of the output with respect to its linear product times, we take the weight vector for layer 1 and we transpose it into a 1 form, and then we have differentiated this as being this term, so we can write that as Jacobian of the outputs of layer 2 times the block diagonal matrix, and when we differentiate this 1, we get a 0. And so we can now write what we wanted, which is we can write this entire gradient. Let's do that. So the gradient of the objective as a function of all of the weights in the entire network is this. We take minus r times, so that's a, let's omit the w. Well, let's put the w in. Times the rate of change of the output activation function with respect to the hidden layers linear product times we take the input to layer 1, that is a function of all of the weights in layer 2, and then we multiply that by the Jacobian matrix for the outputs of the hidden layer times the block diagonal matrix, append a 0 to account for the differentiation of the bias term. And that is the gradient of our objective function.